Yeah, that 80.
Okay, so the lab unit today is fairly straightforward, but there's a couple of glitchy things to it. So I call it the explosion, but the explosion is simply going to be this plunger going out like this. So the ultimate goal of this lab is that, number one, you're going to see this whole idea of conservation of momentum works, and then also see if we can verify Newton's third law of motion that says for every action there is a reaction, for every force there's an opposite force. So on the data table here, wherever there is an asterisk, okay, in that area down below is where I want to see a calculation. It might be something incredibly simple. It might be a number minus 0. It might be 0 minus a number. It might be weight divided by G. But any place there is an asterisk, okay, that's why I tell you, show any calculation in the space provided below the requested information. This is the asterisk. That's where you're going to show. That's not where I want the data written. I want the data up above. I want the calculations in the big space down below. So you're going to have two different carts, okay? One of which you're going to put a 500 gram mass on. These are exactly 500 grams. You don't have to weigh them. These are 500 grams, okay? Don't have to worry about those. Now, you are going to need the weight of the carts. When you weigh these carts using the Newton scales, be careful that the frame of the cart isn't catching on the side of the scale, or you're going to get a false reading. So these are typically around about 5 newtons. So if you're getting something way different than 5 newtons, if you're getting 6 or 7 or something like that, something's gone wonky with how you hooked it up. Okay, so those should be around 5. So when you do this, here's the story. If you didn't have the mass, and you were going to then hit that, let's assume that they have the same mass. If you were to hit this button, what would happen to the carts?
They'll go away from each other.
What about their velocities?
They should be the same.
Why?
Same mass, same amount of force applied to each one, same
Yeah,
velocity.
same mass, everything's the same. So if that's the case, come back here. Okay, let them go flying off like that. Law of conservation of momentum holds true. Yet again, score for the home team. Now, what you're going to do is you're going to put a 500 gram mass on one of these. If you want to take a little bit of tape to secure it, you can. So on this one, I'm going to tell you, securely take the 0.5 kilogram mass to cart 2. I don't care which one you call cart 2 in terms of the plunger, but for this way, when I go to grade this, everything is the same. So what you call cart 2 is going to have the 500 gram mass. It doesn't have to be the one with the plunger on it, but cart 2, this is why we're all the same. Cart 2 is going to have the 500 gram mass. So here's what you want to do. You're going to have a 500 gram mass on this one. You want to adjust the starting position so that when you hit that plunger, they're going to hit the edge of this ramp at the same time. Okay? So here's the question. Do you want that to be this situation where you have the 500 gram mass closer to the edge? Or do you want to be it like this, where the smaller mass is closer to the edge? Preston.
Where the weight's on the one side.
This side?
Yeah.
Why?
Because the one with the weight's gonna move slower.
Why?
Because because momentum, since it has more weight, the other one
Has more mass.
has more mass. It's gonna be moving slower.
To have the same momentum as,
The light one.
which is going to be moving
Faster.
faster. Okay. Now, here's the decision this is where you got to have your phones because you need to time this. Okay. So what you want to do when you hit this button, and we'll talk about energy later, because when you push this in, and by the way, if it won't stay in, like when you push that, there's a little silver tab up at the top. Give that a push. That will help lock that into place. So we'll talk about work. That's the next unit. So the short version is that you all just did work. You exerted a force over a distance and you stored potential energy. Mother Nature doesn't like potential energy. They said something way back on Snapchat, Twitter, or something. I don't know what happened. They don't like each other. Mother Nature and potential energy don't get along. Mother Nature and kinetic energy are besties. Kinetic energy is the energy of motion. It comes from the Greek word kinesis. So, as soon as I hit that button, if Mother Nature liked potential energy, what would happen when I hit that button?
Nothing.
Nothing. It would stay there. Mother Nature goes, cool, I got potential energy. Nice. Okay? And the cart would just stay there. Nothing would happen. Like, well, that just kind of anticlimactic. But that isn't what happened, because of the fact that Mother Nature likes kinetic energy and despises potential energy. So, when you do this, boink, okay, that wasn't far off there. So, here's the decision that you need to make as a group. And I don't care how you do this, but you need to make a decision. You either go off of the back of the cart, so like let's say you'd say the back of the cart is at 102 centimeters. And then you're going to stop it when it gets to 122. The back of the cart is this one is at about 70, and that's going to go to 0. Okay? That's option number 1. Option number 2 is that you start in the middle. Okay? It's like, oh, they're both at 87 centimeters. Boom, they go like this. But then, if you're going to start with the front of the cart, then when you stop it, you have to stop it where the front of the cart is. You can't go, oh, we'll go off the front of the carts and then measure where the back of the cart is over here, because then your measurements are going to be off by the length of the cart. Okay? I don't care how you do it, whether you go off outside to outside or if you go inside to inside. I don't care. Just make sure everybody's measuring from that same point. So, in terms of data collection, boom, do that, you get the times, that's it. That's all the data that you're going to need. The analysis is going to take quite a while. So, spin that around back up on the board. So the key assumption that we're going to make on this lab, and it's a fairly valid assumption, is that as soon as that plunger pushes off, okay, so as soon as that loses contact, we're going to assume that the velocity is going to be constant, okay? We'll assume that it's a frictionless surface. In reality, it's not, but over that relatively short amount of distance, hey, it's a safe assumption that we can make. So, what you're trying to figure out is the velocity, not speed, of each cart. You're trying to find the velocity. So if you go old school, remember velocity is displacement divided by time. And old school displacement is position final minus position initial over time. So on here, because we're also going to be dealing with momentum, so this is why I wrote position initial, position final. Okay, so this, when you see those here on the left side of this grid, that is not the momentum. The momentum is going to be over here on the right-hand side. So these are going to be your initial and final positions. Again, make a decision. Are you guys going to go off the back of the cart and then to the edge of the ramp? Or are you going to go off the front of the cart, but then you've got to figure out where the front of the cart is when you stop it? I don't care. Okay? Pick one. Just make sure that everybody knows what you're going to have going on. So, you're going to know the initial position and the final position. And then you're going to divide that by the time it takes for these things to roll. Because again, basically what we're saying is distance over time equals velocity. And what's the only time you can use that? When the velocity is?
Zero. Constant?
Constant.
Yeah. Well, I mean, if it was zero, it would also be.
Constantly zero. I like it when the velocity is zero because it makes the math.
So, momentum is zero too. What's the problem? Okay. So, on here, where I'm asking you to calculate displacement. Again, it's a simple calculation. It's going to be one number minus another number. It's going to be one number minus another number. So what do you know about the signs of your displacement when you get done? Should they both be the same, or should they be opposite? Opposite signs, because velocity is displacement divided by time. So if you end up with two positive velocities, you have done something horribly wrong. If you end up with two negative velocities, you have done something horribly wrong. Okay. Now, V naught, simple. What's the initial velocity?
0.
0. So that V column, this is where you're going to take that displacement and divide it by that time. So not the delta V, but the V column is going to be displacement divided by time. That's where you should get a positive and negative velocity. Change in velocity. Sum final minus sum initial. Simple math. Initial momentum, final momentum. So to get the final momentum, you're going to take the mass of the cart and multiply it by that velocity. Okay? So you're going to find the velocity. This is the momentum after the explosion. Okay? Change in momentum. Momentum final minus initial. Now, to calculate the force, and I tell you to see question number 2, we're going to use force times time equals change in momentum, which is mass times delta V. For the time calculation of this one, use 0.0200 seconds. Do not use the time that the carts are rolling, okay? Because what we're assuming is that the only time the momentum changes is when that spring is expanding, and that's how long it takes for the spring to expand. So, boom, there's your explosion, only lasts 0.02 of a second. Boom, they're going to go flying apart. And then after that, we're going to assume the velocity is constant as they roll. Okay? So, on that force calculation, on that last column, that's the only time you are going to use the 0.02 seconds. Okay? On your velocity calculation, you're going to use the time that they roll. That's the only time you're going to use that value. Okay. On the front, up there at the top, this is something you all need to hand in. You're only going to hand in one per group. But you're going to sketch, okay, and everybody kind of needs to think through this. Now that you kind of have an idea of what this lab is going to look like. You're going to sketch a velocity time graph for the motion of the cart where time is 0 is the point at which the plunger is released, assuming the carts have constant velocity. After the impact of the plunger, be sure to indicate which cart has the more massive one. So on that pre-lab, y'all, here's the point. Y'all want to get together and say, okay, hey, what would a velocity time graph look like for this situation? Okay? When you get on the back side to question number 8, okay? So on question number 8, I want you to visualize this. Here's the ramp, okay? Now, I'm going to put a small piece of wood underneath one end, okay? So right away, what did I just create? I created an inclined plane at this point. Now, I tell you, I've given you the beginnings of the velocity time graph. And I tell you that the more massive cart has a positive velocity, labeled the point where the more massive cart changes direction. So, here, visualize this. Here's your two carts. Here's the one with the more mass on it. You're going to release the plunger. Obviously, this one's going to go up. This one's going to go down. Okay? When you draw those lines, if you want me to think those lines are parallel, you draw them exactly parallel. If you think they have different slopes, you think one slope is steeper than the other one, you draw it where I can clearly see which one is more steep.
Can we draw a line between, say, parallel?
Yeah,
No,
that's
you
cool.
don't.
When you get to questions 1 and 2 on that application, those you can answer right there. But question number 3 with the bullet hitting the stationary block, those, question number 3, you do on another sheet of paper. Do not answer them here.
Man, you made it way into the alphabet on that one question. It's one question. A, B, C, D, E, F, G, H. That's more notes than there are. Even the notes only go to G. Don't you think you're getting a little bit greedy?
Yes.
Okay, I just had to hear that.
Does this face look like I care?
No. I didn't expect you to.
The worst I go, I think there's one I go to like S.
Oh my gosh.
But it's still only one question.
Why?
Because I can. No, I know there's one like when we at the end with energy, you're going to have one. It's called. Just remember the satellite problem. The satellite problem has the most parts of any question I'll ever give you.
Do you
So
ever get to like A2?
no, I don't get into. I could get into the Greek alphabet, but I've never gone that far.
That would
Okay,
great.
so here's the story. I know
I'm
the
just
Chiefs
giving
play
you
tonight, so I kind of
I'll give you
shortened
one.
this up. So you can get all that stuff done, get your data, and then you're on your own. Okay,
Quick question.
no. What?
Just so I have this right in my mind, a rubber ball, does that transfer more momentum than than like a, cause
Okay,
it,
it isn't about transferring momentum.
or like, cause its velocity goes from positive to negative, it's like a greater
You can talk about changing momentum.
change of,
Okay? So whatever change in momentum, here's the gap Sean theory. Whatever change in momentum one has, the other one has to have
the same,
change in
equal.
momentum. So if this rubber stopper, hold on, let me show you. Let me give you a visual.
Wait,
Which question is that?
Hold on.
Wait.
he
14?
showed us that back there with the rubber ball, like,
Yeah.
I wasn't there for that.
oh, I don't care.
You should have watched the video. I watched part of the video.
Oh yeah, he did show it. What am I doing? Okay.
Sean, can you explain the
Okay.
difference on the
You ready?
B and C?
I'm gonna throw you this ball. All I want you to do is catch it. It's just a tennis ball. Okay, all I want you to do is just catch it. Okay?
Can I try again?
Great. I'm throwing a tennis ball to AP Physics students.
Okay.
Okay, you ready? All right. Throw it back. Now, did you change the momentum of the ball when you caught it?
Yes.
Yes. Okay? Was there a certain amount of force on your hand?
Yes.
Yeah.
Now, I'm going to throw you the tennis ball again, but I want you to use your hand as a tennis racket and try and hit it back to me. Okay. You ready? Now, what took more force?
The second one,
Why?
I felt it. That's circular logic. I think you need to do it again for me to
Okay.
understand.
You ready?
Okay.
Now, just catch it.
Just catch.
Okay? So you took the velocity from some positive value to zero, right? Okay, now throw it back. Now, I want you to hit it and make it come back to me. Okay? Now, with that situation, you took it from positive velocity to zero down into a negative value. So since that was a bigger change in velocity, the tennis ball underwent a greater change in momentum. Your hand underwent a greater change
I
in
would have missed
momentum.
both.
And change in momentum equals force times time. So if you assume that the times are the same,
It's a greater force.
yes. Does that make sense?
Mm.
Okay. Anything else? As you erase,
I should add a sentence.
I just like erase a couple of words and just change them.
I need to erase on
But it's
two.
Are you erasing the rubber bullet one?
greater to smaller.
I'm erasing the rubber bullet and the beanbag rubber ball one.
Oh, the rubber bullet one. Oh.
Oh, yeah.
okay, anything else? Now, once or twice, shut down the yonder camera.